Hi everyone, in this new video we will explain from a visual perspective what a low-pass filter does in terms of delay and noise reduction, and we will show you some examples for this low-pass filter applied to a step signal, a ramp signal, and also to a signal with some noise from real measurements. Our first example will use an step, basically a signal jumping from 0 to 1 at time equal to 0 seconds. And in this case, we have also an step underscore copy signal, which is basically the same. And we are going to apply a low pass filter delay in this second signal and compared to the original one. Now we have an option called first order low pass filter. And if we enable this, we have the option to change the time constant. By default, this is disabled by setting a time constant of 0. Now we can also read the hint for using this function. It reads the Laplace transform block for this low pass filter, but this is not the purpose of this video. If you are interested, we can cover the math behind the low pass filter calculation and even the how it is programmed in the Explorer source code in another video. But let's just see in terms of the plot results how changing the low pass filter time constant affects. For example, let's try first with, in this case, 50 milliseconds. We see that the filter signal is a delay compared to the original one, and basically it is an exponential function. So in the beginning there is a lot of slope, and in the end of the transient, the slope is reduced a lot. So also we can have like change the time constant. Let's say in this case we are doubling it up to 100 milliseconds, and we see that the delay is far lower. And as I said, 0 is like not applying, and for example 5 milliseconds is also quite faster. Let's try, for example, 10 milliseconds, and you will see that the delay is so slow that it does not, in the 5 seconds we have of simulation, it hasn't reached the final value. Let's try with 1 second, for example. Okay, let's see one thing, which is that basically this step and the delay that we have for an step signal is using a low pass filter is like, from a math perspective, is something we can calculate. And indeed there are some like tables for that. For example, related to the tau constant, in this case we are using 100 milliseconds. We can, and that is a general rule we can always apply for an step, is that the low pass filter output, it will be at 1 per tau, in this case 1 per 100 milliseconds, the 63.2% of the step. It would be for any step, but for making things easier, we have just used a step of 1. So 63.2% would be 0.632 in this case, which is at 100 milliseconds. Let us use label cursors. We have here also, already created, but hide it, and you can see 63.8. So basically, approximately, because this is it has a discretization, this signal, we are reaching these values. And let's use all the label cursors we have already created, and let's compare them to the expected behavior here. Okay, we can see the first one, 63, can be perhaps the millisecond before, because in the end is just a discretization, but we are like having the results with enough precision matched. The second one at 200 milliseconds super tau is 0.86, which is 86%. The third one 95%, the fourth one 88%, and the fifth one is at 500 milliseconds 0.993, which is 99.3%. So in general, as a thumb rule, let's say that the comparison between the output of a low-pass filter and the original step response is negligible at 5 per tau, in this case 500 milliseconds. The following example is a ramp. In this case, we have created a signal for a ramp starting at time equal to 0 and 0 units up to time equal 4 seconds 1 unit. So the slope is 0.25 units per second, and we have the same as with the step, the same signal copied. In this new signal, we are going to apply the first order low pass filter. Let us continue with the 100 milliseconds sample, and this is also a general rule you can always use, that is, with a ramp signal, the low pass filter output is always another ramp signal that goes in parallel to the original one, and the delay in, let's say, an horizontal line from one signal to the filter one, the input to the filter, is equal to the time constant, in this case 100 milliseconds. How can we, for example, evaluate this? That can be done using a calculated channel of 0 inputs. Let's say this is 0.5 constant, and for this we are going to have 0.5. basically this is just a horizontal line. Okay, have it here. So now we are going to evaluate. Let us add some label cursors, okay, because this makes things easier. So here we can see with more zoom that, for example, the blue line is crossing the 0.5 value approximately at 2 seconds. It does make sense because the ramp is 0.25 per unit per second and it starts at 0 seconds. And the red line, more or less, it will be at, let me just zoom it a little bit more. It will be exactly at, well, we can say 0 point, perhaps a little bit more or less, but it is like 2.099 if we can move it a little bit more. So in the end is, the delay is tau from 2.0 to 2.100 or 2.1 or 100 milliseconds, as you may want to refer to it. So the point is that this is validated just using a constant horizontal line of 0.5. There's another thing we can do, that it would be creating another, exporting this file, and let's say we can name it as delay. So now we can open it again, is delayed file, and search for the ramp signal. It will be the same, but now in this new channel we can apply a time delay. This is more for benchmarking purposes, but in this case it will be the same. Okay, so now you can see that in this case the orange line is exactly at the same point as the red line. So let me zoom out. So here you can see that it is exactly the same. So for when the filter is stabilized, they are perfectly parallel. But at the beginning, as you can see, it is not perfectly parallel, but this is from the mathematical perspective and the formulas behind this, it is the expected behavior. And also in the end, the parallel line will be the orange one, but at the end, since the input is not increasing in a ramp anymore, this is more like the results we have seen in the first example with the step. In this third example, we are going to use the low pass filter to reduce the noise of a series. in this case, this is a hardware in the loop results for a simulation that it is also performed in PSSE. In PSSE, the results are by far more ideal, so there is no noise, like the commutation noise of an inverter. The point is that we have also added the same signal from a copied channel file just to see the implications of the low pass filter and compare to the original value. Let's try also, for example, let's start with a very small filter, like 5 milliseconds. Okay, let's see, for example, in this region. Okay, so it's more or less the same. So perhaps we need to increase it. Let's say 50 milliseconds. Okay, here we can see that there is still some noise, but we have reduced it from the original one. And again, we are going to use 100 milliseconds. And in this case, let's see now, like we don't have much noise. I would say that this the most appropriate value for this test, just to compare both signals, PSSE and the hardware in the loop. In any case, let's do something else, which is to add a very long low pass filter. Let's say, just for illustration purposes, let's add 5 seconds. So now we can see the other implication of using a low pass filter. One is for sure reducing the noise, which is positive, for example, in this case, and the other one is applying a very long delay if we increase it too much the time constant. For example, in this case, it is quite easy to observe that we are applying let's say the original value would be like a step with some noise, but very fast at the beginning. And here with a very slow low pass filter, in this case it was 5 seconds, we see a really slow delay. And with this very long delay, for example, in this step, we don't even see the delayed measurement or the delayed series even reaching the steady state, and before we apply another step, in this case another voltage step. So let's see, in this case, let's go back to see the effect of, for example, 5 seconds is too much, 1 second still too much, and you can play with this and search and find the most appropriate value. In this case, as I said before, I believe 100 milliseconds is something reasonable because it adds a little bit slower, slightly delay, let's say, but not too much for if we see the simulation in this case with some zoom out, but we reduce all the noise from the original one. Well, that was everything we wanted to cover in this video. It was a long one compared to the previous one, but hope you found it interesting. And if you want to be updated with new videos we will upload in the future, please consider subscribing to our YouTube channel. See you in the next video.